Although the WLW 500,000-watt transmitter officially went on the air in 1934, we must begin some years earlier with a bit of background on the man behind this project and the events leading up to its inception. Powell Crosley Jr. was born in Cincinnati, Ohio in 1886 and grew up in the College Hill area of the city. In 1921, he became interested in radio when the first broadcasting stations went on the air. His son wanted a radio receiving set so he could listen to this wonderful new invention. When Mr. Crosley took him to the neighborhood radio store to buy one, he found out that the cost of a commercial receiver was $130, a lot of money at that time. So instead, he bought a book on how to build a receiver. When he and his son built a crystal set and began listening to the few stations then on the air, he was dismayed at the irregularity of broadcasts and the poor quality of programs available. In addition to the presently available radio receivers being too expensive, he was acutely aware that there were too few broadcast stations which could be received reliably in the Cincinnati area. And so began Mr. Crosley's pioneering career in radio broadcasting, which gave birth to many innovative concepts both in engineering and programming. In the spring of 1921, he began his broadcasting experiments. In July of that year, he was granted an experimental license for this transmitter with call letters 8CR to operate with 20 watts. Shortly thereafter, he received permission to increase his power to 50 watts. His first broadcast was from the living room of his home, located at the corner of Davie and Larch Avenues in College Hill. He played a phonograph recording of one of his favorite selections, Song of India, several times and requested that anyone hearing the program send him a postcard. He received several responses, including one from a man living on the east side of Cincinnati and one from Troy, Ohio. This was all the encouragement he needed. He began to envision a nation dotted with powerful broadcasting stations, through which, at all times of the day and night, by the twist of a dial, people could bring into their homes a variety of entertainment, musical, and informational programs. Mr. Crosley continued his experimental broadcasts, and a few months later moved the transmitter to his family's phonograph cabinet manufacturing plant on Blue Rock Road near Knowlton's Corner in Cincinnati. In March of 1922, he received authorization to increase power from 50 to 500 watts. This is part of the license granting the use of 500 watts, along with the assignment of the call letters WLW. The station shared two operating frequencies, 833 kHz and 619 kHz. The higher frequency was to be used for entertainment programs, and the lower frequency was for weather and farm information. In 1923, he consolidated his broadcasting activities into a new company, the Crosley Radio Corporation. As the broadcasting business grew, it was moved to Alfred Street. Mr. Crosley is shown at the Alfred Street transmitter. In January of 1925, he was granted another tenfold power increase to 5,000 watts. This required the transmitter to be moved to a more rural location in Harrison, Ohio, 22 miles west of Cincinnati. He purchased a farm, installed the transmitter in the farmhouse, and erected an antenna on the site. This transmitter site was unique. It was the first time a transmitter was remotely located from its studio facility. 2.5 years later, on July 1st, 1927, he was granted the use of the 700 kHz frequency. Then, on May 25, 1928, the Federal Radio Commission, predecessor of the Federal Communications Commission, granted WLW authority to construct a 50,000-watt transmitter. 5 months later, the first commercial 50,000-watt transmitter placed in service in this country, a Western Electric Model 7A, was installed at Mason, Ohio. It was co-located with the WSAI transmitter, the station which Mr. Crosley had recently purchased from the United States Playing Card Company. This is the 50,000-watt transmitter. Its serial number is 105. As transmitter technology advanced, receivers were keeping pace. Even before he began his broadcast experiments, Mr. Crosley had seen the need for lower-cost radio receivers. This is one of the early crystal sets. In late 1921, he purchased the Precision Equipment Company and began designing and producing economical radio receiving sets. This one-tube receiver, named the Crosley Pup, was one of the most popular receivers, which sold for under $20. He relied heavily on the technical expertise of his chief engineer, Dorman Israel. This typical production line at the Crosley plant incorporated the mass production techniques developed by Henry Ford. Mr. Crosley's business philosophy was to market the lowest-priced radios possible, so they could be affordable to families with modest incomes. This is how he was able to develop a radio and market it for under $20. When he started production, he employed mostly male workers. He soon converted the production line to female workers because of their better manual dexterity. By the spring of 1922, he was producing 500 radios a day in the largest radio manufacturing plant in the world. It was in this Crosley development lab that the radios were designed and tested. The engineer in the lower right corner is E.J.H. Bazard, who worked closely with Dorman Israel. Typically, families eagerly gathered around those early receivers. To improve the performance of these low-cost receivers, Mr. Crosley recognized the need for even higher power transmitters. In the early 1930s, he began dreaming of another tenfold increase in transmitter power to 500,000 watts. A construction permit was issued, and work began. The official license to operate on 700 kilohertz with a power of 500,000 watts was granted on February 9, 1934. He contracted with RCA to serve as prime contractor for the design and construction. RCA subcontracted much of the work to General Electric and Westinghouse. General Electric was responsible for the design and construction of the radio frequency amplifiers, DC power supplies, high-voltage rectifiers, harmonic filters, RF transmission line, antenna tuning equipment, control systems, and control console. GE engineers assigned to the project were Edward A. Leach, George W. Filer, and Ray H. Williamson. Westinghouse was responsible for the audio frequency amplifiers, modulators, modulation transformers, filament supplies, isolation switching, motor generators for circuit controls and bias, water cooling pumps, heat exchangers, and the entire cooling system. Westinghouse engineers assigned to the project were John A. Hutchison and Gerald V. Bate. RCA, as prime contractor, was responsible for coordination with all the subcontractors and, as you see, put their name on the nameplate. The design and construction began in January 1933, and components were shipped to the Mason, Ohio site in August of 1933. During this time, the Blaw-Knox Company in Pittsburgh designed and began erection of the 831-foot cantilever guide vertical tower. By December 1933, the amplifiers were installed, and testing was conducted during the experimental period between 1 a.m. and 5 a.m. This is the front of the transmitter during the latter phase of construction. The entire unit is 54 feet 7 inches wide, 13 feet 2 inches high, and 17 feet deep. The three sets of doors on the left are the three power amplifier cubicles. The next two are modulator cubicles, and the one on the extreme right is the rectifier. In the back of the transmitter, pairs of metal-lined doors provide access to the rear of each of the 6 cubicles. The door to the rear of power amplifier number 1 provides access to the spiral coupling coil, the variable plate tank coil, and the fixed plate tank capacitor. Note the Faraday shield and the 1-inch aluminum pipe construction of the plate tank capacitor. Power amplifiers number 2 and number 3 are of identical construction. Behind the rectifier cubicle, the relays for the control circuits are panel-mounted. At this point, it should be made clear that the 500,000-watt transmitter utilized the 50,000-watt transmitter as the radio frequency driver for the 3 power amplifiers. In the foreground is the control console, and to the left, the 50,000-watt transmitter. The cubicles to the right house the 3,000-volt bias rectifier. The radio frequency section was comprised of 3 separate power amplifier units with switching capability of isolating one or more of the amplifiers. Each power amplifier used 4 Type 862 triodes, rated at 100,000 watts plate dissipation. They operated in a push-pull parallel Class C mode. The output coupling coils of each unit were in series. The 3 power amplifiers were high-level plate modulated by 2 modulators, each containing 4 Type 862 triodes in a push-pull parallel Class B mode. The 2 modulators were driven by the modulator in the 50,000-watt transmitter. The complete transmitter utilized 22 Type 862 tubes, 2 in the RF driver, 12 in the power amplifiers, and 8 in the modulators. The high-voltage rectifier was 3-phase full-wave, incorporating 6 Type 870A mercury arc tubes, rated at 60 amperes each. Note the size of the DC generators. They supplied the 4,000 amperes required to light the filaments of the 862 tubes. In 1935, the 862 tubes with their antiquated DC filaments were replaced with 898A triodes with 3-phase 6-wire filaments. These tubes were rated at 90 amperes emission with an amplification factor of 45. Their filaments were multi-strands of pure tungsten and could function on DC, single-phase, 3-phase, or 6-phase. They required 28.6 volts phase-to-phase and drew 140 amperes, which totaled nearly 7,000 watts of filament power for each tube, or 150,000 watts for all 22 tubes. The AC filaments of each 898 required 3 single-phase, high-reactance transformers with 240-volt primary and 16.5-volt, 140-ampere secondary. The transformers were designed with high reactance to limit the startup current to 200 amperes with cold filaments. Each transformer was 13 inches high, 10 inches wide, 8 inches deep, and weighed over 150 pounds. The secondaries were wound with copper conductor, 3/4 inches wide and 1/4 inch thick. 60 of the transformers were mounted on a structural bridge in the basement to minimize the lead length to the tubes directly overhead on the main floor. The 60 filament transformers weighed almost 5 tons. The tubes generated a tremendous amount of heat, which required a sophisticated cooling system. Distilled water was pumped around the anode at 20 gallons per minute, plus 15 cubic feet per minute of air blast on the filament and grid seals. This totaled 70,000 watts of plate and filament dissipation per tube. The 22 tubes, with 20 gallons per minute of pure distilled water flow, required 2 50-horsepower pumps capable of pumping 440 gallons per minute. A plumbing network consisting of 50 feet of 1.5-inch Pyrex pipe was connected to the inlet and outlet of each anode water jacket to isolate the 15,000 volts. This totaled nearly 1/2 mile of Pyrex pipe. The heated, distilled water was pumped through 2 Westinghouse boiler-type heat exchangers, which in turn were cooled with 1,500 gallons per minute of raw water. High-temperature water stills operated continuously to maintain the quality and quantity of the distilled water. The raw water was pumped into a 70 by 70-foot spray pond to dissipate the heat and was recirculated back to the heat exchangers. Notice the 16 spray nozzles. The glass 870 rectifier tubes were replaced with metal 870A tubes for better cooling and longer life. These were rated at 15,000 volts and 60 amperes. Their filaments were single-phase, 5 volts at 65 amperes. Frequently, these tubes would arc back. The best estimate of the peak inverse surge current during the arcing was 4,000 amperes. These arcbacks would be felt over the entire electric power network. Primary power was supplied to the transmitter site by 2 separate 32,000-volt circuits, one from the east and one from the west, to assure uninterrupted service. This substation transformed the voltage to 2,300 volts, which was fed underground to the transmitter building. 3 power transformers of 430 kVA were controlled by large breakers, so their primaries could be connected in a Y formation for startup and a delta formation for full power. The filter reactor was a quarter Henry at 125 amperes. It weighed 3,190 pounds and was cooled with 160 gallons of oil. The modulation reactor was 4.5 Henrys at 60 amperes. It weighed 9,500 pounds and was cooled with 525 gallons of oil. 2 modulation transformers were required. Each unit was rated at 180 kVA from 30 to 10,000 hertz. The primaries were push-pull, 6,365 volts each side. The secondary is 4,250 volts. The 2 in series developed the 8,500 volts RMS necessary to modulate the radio frequency amplifiers up to 100%. Each modulation transformer was 8 feet high, 6 feet wide, and 5 feet deep, weighed 35,700 pounds, and was cooled with 725 gallons of oil. Now that you're familiar with the size of the components and the brute force engineering involved, let's go through the startup procedure. First, turn on the rectifier filaments so that the ambient temperature in the rectifier cubicle will reach 90 degrees. Next, turn on the filaments of the 8 tubes in the 2 modulators and the 12 tubes in the 3 power amplifiers. Then, set the circuit breakers in the Y position for the power transformer primaries. Proceed through the following checklist. 1. Check water flow through each 898 jacket. 2. Turn on all the 898 filaments and observe each filament strand through dark welding goggles. 3. Check bias voltage to each power amplifier for 3,000 volts. 4. Apply plate voltage to power amplifiers and modulators. 5. Switch the 50,000 watt transmitter to its function as a driver for the 500,000 watt amplifiers and check tuning and coupling on each of the 3 power amplifiers. 6. Change the primary breakers to the delta settings. 7. Increase the modulation to normal levels. 8. Recheck tuning and get a great thrill in dipping the plate currents to 100 amperes. The total output of the 3 power amplifiers is fed to a harmonic filter, then into a 100-ohm air dielectric coaxial line. The RMS unmodulated radio frequency current at this point is 70.7 amperes. The 800-foot transmission line enters the coupling house at the base of the 831-foot tower. It is matched through an L network to the 390-ohm base impedance of the tower. The tower base current of 35.7 amperes produces 500,000 watts output, which creates a field intensity of over 6 volts per meter at 1 mile from the tower. The half millivolt per meter contour was about 300 miles from the station. The tower base insulator supports 110 tons of steel, plus 340 tons of vertical component of guy wire tension, for a total of 450 tons. Notice the ball gap for lightning protection and the rifle barrel photoelectric cell to trip the high-speed breaker to deionize the gap. This was necessary because the transmitter power was sufficient to sustain the arc once the gap was ionized. Everyone is aware of the power of lightning. Here we see the dramatic effect of a direct hit on the steel ball on the flagpole atop the tower. Various measurements were made to determine the amplitude of the lightning current. WLW engineers measured currents as high as 40,000 amperes. It first went on the air as a commercial station on April 17, 1934, and operated full-time until March 1, 1939, when Senator Burton Wheeler of Montana railroaded a resolution through the Senate limiting the power of commercial U.S. broadcast stations to 50,000 watts. This was done on behalf of Ed Craney, one of his constituents, who owned and operated a 250-watt local station and wanted to obtain a license to operate with 50,000 watts on WLW's frequency. WLW appealed, and it was decided that it could retain its clear channel status. However, from the time of that 1939 Senate resolution onward, the 500,000-watt transmitter was limited to experimental, non-commercial operation from midnight to 2 a.m. And so, at midnight, the WLW studio announcer would say, "We ask your indulgence a moment while we make transmitter adjustments to operate with 500,000 watts under the experimental call letters of W8XO. One moment, please." And each night, the first program broadcast was the well-known Moon River, whose familiar opening poem began, "Moon River, a lazy stream of dreams, twined in the hair of night." Finally, in late 1943, experimental authorization expired, and this great pioneering effort in broadcast transmitter technology ended. By 1944, Mr. Crosley lost interest in broadcasting and turned his attention to other pursuits, such as the manufacture of appliances, production of small automobiles, and the Cincinnati Reds baseball team. In 1945, he sold the broadcasting and manufacturing companies to Avco Corporation, while retaining his ownership of the automobile plant and the baseball team. During and beyond the time of WLW's 500,000-watt operation, efforts for the use of higher power for commercial broadcasting continued. The licensees of a number of Class 1A clear channel stations organized to perpetuate the concept of high-power, clear channel skywave service to the entire population. This map, prepared in 1960, shows what the daytime coverage of WLW would be with a proposed power of 1 million watts. The three types of daytime ground wave service are grades A, B, and C, as shown by the red, orange, and yellow areas. During the daytime hours, these services are limited by rural man-made noise, urban man-made noise, and adjacent channel interference. For grade A service in rural areas, a ground wave signal of 1.5 millivolts per meter is required. For urban service, the signal must be sufficiently strong to override the man-made noise and serve 90% or more of the population. For grade B service, the ground wave signal of a half millivolt per meter is required, and in urban areas, 70% of the population would be served. For grade C service, a ground wave signal of 1/10 of a millivolt per meter is required. In urban areas, this would reach 50% of the population. The white areas within the B and C contours indicate loss due to adjacent channel interference. For comparison, here's the 50,000-watt coverage of WLW using the same criteria for the A, B, and C contours. It's interesting to note that the major urban areas of Columbus and Indianapolis are well within the grade A contour, yet only 70% of their population can be served because of the interference from urban man-made noise. One of the main arguments for higher power was to offset the substantial increase in man-made noise. Electrical appliances are the main cause of this interference. To illustrate this, notice the rapid increase in electrical energy consumption between 1938 and 1958. Since most electric appliances generate some form of electrical noise, the result was an increase in interference to AM radio reception. Note that rural electric energy consumption increased far more rapidly than urban consumption. The black areas on this map indicate where AM nighttime ground wave reception was available as of 1957. The white areas are locations where no nighttime ground wave reception was available. The people living in these white areas depended entirely upon the skywave service from clear channel stations for their nighttime reception. It's interesting to note that even today, the white areas remain virtually unchanged. Over 75% of the population residing in the white areas lies east of the Mississippi River. In 1946, the FCC initiated hearings to determine the future of AM broadcasting, particularly focusing on clear channel stations. These hearings, designated as Docket 6741, would drag on for many years. In 1960, the FCC reopened Docket 6741 and proposed assigning additional stations to some of the channels. WLW joined with other clear channel stations in opposing the plan. In addition, they presented detailed exhibits showing that a better method of providing nighttime reception to the white areas would be to maintain the clear channel concept and permit them to increase power to 1 million watts. This would be the average nighttime coverage of WLW when operating with a power of 1 million watts. The previously mentioned ground wave service remains nearly the same as the daytime map, except for the distortion or selective fading zone, which limits reception approximately 100 miles from the station, because the ground wave and the sky wave are nearly equal in intensity. This area is represented by the yellow ring covering parts of Ohio, Indiana, and Kentucky. The nighttime coverage is represented by types D, E, and F reception, as shown in the cross-hatched red, orange, and yellow areas. The D, or red area, represents the most reliable service expected to be available 90% or more of the nights of the year. The F, or yellow area, represents the least reliable service, expected to be available only 50% of the nights. Adjacent channel interference is also a factor, but is not shown on this map. The red area on this map shows how WLW, with a power of 1 million watts, could cover a substantial portion of the existing white area in the eastern part of the country. This coverage is based upon average atmospheric noise data. Nighttime atmospheric noise is the predominant limitation to skywave service. Atmospheric noise varies greatly with the seasons, being lowest in the winter months and highest in summer due to thunderstorm activity. The prediction of atmospheric noise was based on a report published by the International Telecommunications Union in Geneva. A portion of the data was gathered by WLW engineers who made continuous chart recordings of atmospheric noise for many years at a site near Cincinnati. Here we see the nighttime field intensities, which would be required in the summer to override atmospheric noise 50% or more of the time. Recall the map showing the proposed WLW nighttime coverage at 1 million watts. For comparison, this map shows the nighttime coverage at 50,000 watts. You'll notice that there is no red or D-grade service at this power. To illustrate how coverage varies with seasons, this map shows the predicted winter nighttime coverage. From this you can see why WLW, which had similar coverage with 500,000 watts, became known as the nation's station. In 1960, as convincing as the arguments in favor of high power on AM radio seemed to be, FM and television had become major factors, and AM radio no longer was the dominant communications medium. The FCC began to assign additional stations on some of the clear channel frequencies, and the long quest for high power for AM radio died. This program was researched and written by Clyde G. Hanley and Edwin B. Dooley, both of whom were registered professional engineers in the state of Ohio. As engineering executives with Avco and Crosley Broadcasting, they worked extensively on the 500,000-watt engineering and the litigation aspects of the Clear Channel high-power proposals. I'm your narrator, Bill Myers.